Thank you very much. I'm happy that I still have a big audience. And as I promised, in the first part, I will show you how to calculate the color zones in the case of the figure note following Ilia's description of R matrix. And in the second part, I will give a proof of the volume conjecture, a possible way to prove the volume conjecture. And in fact, Tomotada Otsuki followed this way to prove the conjecture in the case of 5.2, 6.1, 6.2, and 6.3. And so hyperbolic notes with small crossings. So it may work, but it is very hard. So let me start. So in this talk, in the first part, I will use a braid description of a link. So it is well known that due to Alexander, any knot or link, but in this talk, I will just consider knot. Any knot can be presented as the closure of a braid like this. So this is my figure knot, and this is sigma 1, sigma 2 inverse, sigma 1, sigma 3 inverse. And if we close it in this way, we have the figure knot. Do you understand? Maybe. Anyway, it is alternating with 4 crossings, so it should be the figure knot. Never mind. And these are generators, and these are relations. And Markov's theorem is that two different braids can give the same knot, and but a knot can be presented to different braids, but they are related in the following 2 ways. By moves of first conjugation, it is just change the part. So alpha, beta, R. So I compose alpha and beta, put beta under alpha. So my string goes from top to bottom. Ilia goes from bottom to top. And the second Markov move is this one, stabilization. So if beta is in Bn, if there are n strings, then beta sigma n or sigma n inverse is in B of n plus 1. So we add 1 string and make 1 crossing like that. You see that if we close the last one, we get this one. And Yang-Baxter operator is okay, so it's better to show everything first. So let V be an n-dimensional vector space over C, and R, this is an R matrix. This is an endomorphism of V tensor V to itself. And we need one more thing, mu. This is isomorphism from V to V itself. And I will show you. This corresponds to, I think, this corresponds to, this is cup. Yes, this corresponds to cup in this way. So I will put mu here. And, oh yes. And this corresponds to R, and this corresponds to R inverse. And and we need 2 more things. A and B are complex numbers. And the first, this equation is called Yang-Baxter equation, and this corresponds to the braid relation, like okay. And this one means that so if we put I'll show you diagrammatical explanation later. So this means mu tensor mu commutes with R, and maybe it's better to show the picture here. So if we have R matrix, then replacing each crossing with R or R inverse, we get a homomorphism from V tensor, threefold tensor V to itself, like that, which I write phi of beta. Beta is a braid. And our link invariant is defined as follows. So given a braid, we close it, and we replace each crossing with R or R inverse like this, and put mu at the bottom. So if we have 3 strings, we put 3 mu's. And because mu is just a homomorphism on V, so from here we have threefold tensor, and so we have a homomorphism from V fold tensor to itself, like this, and we close it. Close it means, so we have a kind of homomorphism from here to here, and we contract this string first, and then contract along the second and the third. It means we take the third trace. Trace 3 means we close here, and trace 2 means we close here, and trace 1, this is just a usual trace. Because if we close 3 strings, then we have 1 string which is a homomorphism from V to itself, so we can take usual trace. This is just a sum of diagonals. And for adjustment, we need divided by B to the number of strings and A to the rise of beta. In the case of the braid, rise, W is simply the sum of exponents. So this is our link invariant. To check the invariance is easy. So invariance under braid relation. So we need to check that the this T is invariant under Markov moves. Markov move is braid relation plus conjugation plus stabilization. So the braid relation follows from the Yang-Baxter equation, and invariance under conjugation follows from the commutativity of mu tensor mu and V. So because mu can go through V, so we can exchange threefold tensor of mu and phi of beta. No, the other way. We go trace is invariant under conjugation. So we can trace is invariant under conjugation means that we put alpha through the top to the bottom like this. So this is because trace is invariant under conjugation. And because mu tensor mu is commutative with R, we can pass the mu's through phi of alpha. So we get that one. So this means that T, our invariant, our value T is invariant under conjugation. Okay. And this shows the invariance under stabilization. So by the second Markov move, we put 1 crossing here. It can be R or R inverse. And look at here, and because the property of the last property, we have the trace 2 of R times identity. So R times identity tensor mu is in the red circle. So this is just a scalar times identity. Means that we have AB here. So this means that if we adjust this scalar by A to the something and B to the something, this whole thing is invariant under 2 types of Markov moves. So so all we need is these 3 conditions. And if the quadruple R, mu, A, and B satisfies these conditions, this quadruple is called an enhanced Yang-Baxter operator. So this is essential part is this R matrix together with some more condition. So if we have an enhanced Yang-Baxter operator, we can construct a link invariant. Then how to construct a enhanced Yang-Baxter operator? To do that, we use a so-called quantum group. But it is well known that given the D algebra and its irreducible representation, one can construct an enhanced Yang-Baxter operator, and it is called GV quantum invariant. Right. In Japan, we call this Ge as German, so Ge V invariant, and SL2C Vn is called the n-dimensional colored Jones polynomial, where Vn is the irreducible n-dimensional representation of SL2C. And yes, and if n is 2, this is just the ordinary Jones polynomial with some replacement of parameter. And this is a precise formula for the R matrices, R matrix, in the case of SL2C and n-dimensional irreducible representation. So we write R matrix in this way. So let me see, EI, yes. So because V is n-dimensional, we have n basis element, which I denote by E0 up to En-1. And the image of R matrix of EK tensor EL is given by this R matrix R IJ KL. And this is the precise formula. It is rather complicated, but and here's the formula for the mu. This is just a matrix, so this is diagonal matrix. So I said that T is an invariant, but we normalize it so that the value for the unknown is 1. Because if we calculate the invariant for the unknown, it is simply the trace of mu, and mu is just a diagonal matrix of these entries. So this is just curly n over 1. Remember that curly n is this one. So okay. Now, from now I will show how to calculate the Color-Jones polynomial by giving an examples. Before that, I will show you some technique. So in the definition of T, we have taken traces of all the strings, meaning that we take all the sums along each string, but we can leave one string without summing because by Schwar's lemma, because this is just a scalar and the representation is irreducible, so this is just a scalar multiple. And so because we fix I here, so and we can consider the image of EI, and if we start with EI, we end with scalar multiple of EI, and which I denote by S. Then what is S? Because the invariant of a given link L is just what is that? Trace of L. Mu times phi. Yes. So okay. So we denote small phi, the capital phi of beta. Then the invariant of L is just a trace 1, trace 2, and trace 3 of phi are composed with mu. Yes. So we need to put mu here. But phi mu. Yes. So let me see. Sorry. Phi is this part. Phi is the linear map from V to V itself. Sorry. And by definition, the value of t is just phi composed with mu and then take the trace. So this is the definition. And then what is this? Because phi is just a scalar multiple by s, multiplication by s. And the trace of mu is just this one. So we conclude that the Color-Jones is simply the scalar times some q to the power. So remember that s is the scalar multiple of this string. Now I'll show you some practical method, practical way to calculate the invariant for the figure-8 knot. This is I was taught this technique by Tan Le. So remember from the formula of the R matrix, we see that yes. So because there is a Kronecker delta, we see that the surviving term is such that the sum of I and j, I plus j is what? I plus j is just k plus L, okay, from this Kronecker delta. And moreover, because m is positive, I is greater than or equal to L, and j is smaller than or equal to k. So if because we replace the positive crossing with the R matrix, so we label each arc. When I call arc, it is separated by the crossing. So we have 4 arcs around crossing, and we label arcs when the value for the R matrix is non-zero. So it is non-zero only when I plus j is equal to k plus L, and L is greater than or equal to I, and k is smaller than or equal to j. Did I say something wrong? Anyway, I will follow this condition. And for the negative crossing, the same is true for the sum, and in this case, L is smaller than or equal to I, and k is greater than or equal to j. Okay. So we start with this figure-8 knot, and we closed the 2 strings, and we keep the first string open, and we label the first string by n minus 1. The labels are from 0 to n minus 1. And then by Schur's lemma, this one should be n minus 1, the same one. And this one is also n minus 1 because L is bigger. But L is bigger, but at most n minus 1. So there's no choice, no other choice. This should be n minus 1. Okay. And then we choose I arbitrarily. And then this should be I because the sum of I plus n minus 1 should be equal to n minus 1 plus something. So this should be I. And then choose j, and then choose k, then just this should be that one because the sum is equal to that one. And similarly, we have this value because j is the same as here. Okay. Now, because the inequality where because which one? I is smaller than this one, and n minus 1 is smaller than this one. So we conclude that j should be equal to k. So we have this, we only have 1 to 2 labels. So this simplifies very much the calculation. Therefore, the n-dimensional Carl-Jones polynomial of the figure 8 knot can be calculated in this way. I put r for the crossing here, and the subscriptions are n minus 1, I, and n minus 1. And here we have r inverse and n minus 1, j, n minus 1, and j, and so on. And from the concrete formula of the R matrix, we get this. This is still something complicated, but the summation is just from for I and j, and I is greater than or equal to j because of the some condition here. So, but still we have two summations. We need to make it one. How? There's another way, a better way. So here we leave the first one open, but there is another technique to leave the second open. This is not a kind of braid-like thing, but this is a tangle. And the labeling is, we need some technique, but the idea is similar. We use the Schwar's lemma, and this is just a scalar multiple. And in this case, we put mu here like this. And for the cap, this is cap. For the cap, we put mu inverse. And then you see that and we put mu inverse, and to put mu, this is just straight line. So we need to put mu inverse here. The mu inverse is easily given from the formula of mu. And doing similar game, we see, but we start with 0 here, because this is positive crossing, and this is smaller than 0, which should be 0. So then doing the same one, we have this labeling. So we have this. We still have two summations, but there is a interesting formula by reducing this summation into 1. This can be easily proven by induction. Try it. So this one can be changed into a single, very simple summation formula. So this way is given by Tanley, and the other way I did not explain, but there's another way using linear scaling theory by Kazuo Habiro. So they give, of course, the same formula, this simple formula. Okay. And then, so yesterday I used this formula to prove the volume conjecture. Yes.
Is it clear that that's a positive sum?
Sorry?
Is it clear from this formula that that's a positive sum?
Not so clear. So if you are not good at this curly braces, so changing this into Q, then it is clear. Anyway, so in the rest of my talk, I will show you a possible way to prove the conjecture, but it is only for the hyperbolic knots. And I will use a technique, a similar technique described by Abhijit, and also by this formula of I matrix. So from this, as Ilya told us that R matrix contains many of these n factorial, or how do you call it? Quantum integer factor, quantum factorial. And so so the color zones is a big sum of labeling of the product of crossings of R matrix very roughly speaking, it is just this one. So for each labeling, we have a big product of R matrices. And R matrices look like R matrix involving this K factorial. So I first show how to approximate this K factorial for large N. So from now, this is very, very non-rigorous description. So please put your spit on your brows. So in Japan, we do it. If your friend will talk you a lie, do not cheat me. Okay, and then so remember. In the volume conjecture, we replace Q with n through the unity, and so the K factorial times n minus K minus 1 factorial. So remember that. Oh, I don't remember. Q to the this one. So some power of Q, or I call it just Q. I write it as zeta sub n, but I simply call it Q. So over something, I forgot.
Square bracket. The square one was written down.
Right? I think it is. So simply just this is just equality here. 1 minus q up to 1 minus q to the k, because if we remove the factorial, the power here, and then 1 minus q up to 1 minus q to the n minus 1 minus q. Okay, and because q is the nth root of unity, we can replace this one with k plus 1, and this one with n minus 1, and this becomes this. Okay. And oh, what is this? Yes, this is just the formula of exponential by using cos and sine. This one, and 2 to the n minus 1 appears because okay, yes, and there is a magical formula. I hope you know it. This product turns out to be n. Just try some thing. So, and we write zeta sub k plus of this product and zeta sub k minus of this product. Then the product of k plus and k minus is just the power of zeta times n. let me see. What is that? K factorial. Yeah. So K factorial is just a power of zeta times zeta sub K plus. So K factorial can be replaced with some power of zeta times zeta sub K plus. And n minus 1 minus K factorial is power of zeta times zeta sub K minus. These are equalities. So this is correct. This page is correct. And from the formula of the R matrix, we can forget this part, power of K, and the R matrix is essentially of this form. There are 5 Q factorials here. So using the formula before, this is just the power of zeta times n squared, and L can be replaced with, let me see, L minus, because, let me see, yes. So K plus times K minus is something like n, okay? So this corresponds to L plus. L plus is equal to n over L minus here. And this is K minus, okay? K minus is just n over K plus. And here we have I plus and M plus and J minus, okay? So our matrix can be written in this form. Similarly, R inverse is of this form. Therefore, from this one, the Color-Jones are, very roughly speaking, Color-Jones is just a sum of product of power of zeta times n over these zeta sub m plus or minus, okay? Now, so this is a very non-rigorous. So what was zeta K plus? It is 1 minus zeta n plus 1 minus, yes, this one. So taking log, product turns out to be summation, right? And remember that zeta is just an n through to infinity. To the n comes here. To the j comes here. And replace x with, j over n with x. Then, this is very strange. Just forget subtle things. Just simply, we simply replace the summation into Riemann integral. This is not true, okay? Never trust me, okay? We replace this with Riemann integral. This is very dangerous. And so log of zeta sub K plus can be replaced very roughly into this n over 2 over pi times something. This, you know this, you remember this. No, you don't, you may not know it. But this is called dilogarithm. This integral is called dilogarithm because if you take expansion by using Taylor expansion and integrating term by term, we get this power series. And remember that logarithm of 1 minus z can be have a similar power series. So I think this is why we call it dilogarithm. By the way, so I think Abhijit told me that the hyperbolic ideal hyperbolic triangle is parameterized by a single complex parameter, and whose volume is given by Rogers dilogarithm. Yeah. So this is d of z, and we write log term in gray because I want you to forget it. So, but anyway, remember somewhere in your brain that there's something remains. But essentially, this is just simply imaginary part of dialogue. So, we want to remind you that we are doing something related to volume of hyperbolic tetrahedron. So, log of zeta sub k plus can be very, very roughly approximated by this dialogue function. Okay, and similarly, yes. So therefore, taking exponent, we have this one, and just forget dialogue of 1. This is constant, and we want to know large n limit, so we can forget just constant. And similarly, k minus can be approximated by exponential of dialogue, but yes, here's inverse. Okay. Now, taking everything into account, our Carl-Jones polynomial can be very, very, very roughly approximated by this one. We forget log terms. Then essentially we have these dialogue terms. Okay. And yes, we just forget log term. So essentially dialogue appears for each R matrix. We have 5 dialogue functions, and I, J, K, A corresponds to arcs, strings coming to the crossing and going out from the crossing, I, J, K, L. And M is another parameter. It measures the difference between I and L. Okay. Now, this is just a big summation, and we'd like to replace summation by integral. Then, so we put v function like this, and then replace zeta to the some power by z. So remember that so if we define v function like this, then I1 up to IC corresponds to arcs on diagrams or the braid. So something like IJKL. And also M inside. And we want to know, so remember the volume conjecture formula. It is log of Jn divided by n. So if we want to know the limit of this form, we can forget log term, our polynomial term. So we can throw this away. Then we essentially have, we can regard that just the Carl-Jones is of this form. So the variables are, we replace this variable with zi, z1 up to zc, where c is the number of arcs. And moreover, we want to replace the summation into integral. This is a very hard part, but there's some technique to replace the summation into integral. In the previous sheet, when we introduced dialogue, we simply change summation into integral, Riemann integral, something like that. So just replace, we want to replace the Carl-Jones into this big integral. Now, we use the so-called saddle point method to approximate this integral. This is a very formal statement of the saddle point method. If we want to estimate this exponential, estimate the large n limit of this one, then we look for the point where the derivative of h function vanishes. And then this is a subtle thing. Then roughly this integral can be, this is a rigorous statement. This can be approximated by this value for large n. I'll give you a very rough idea of the proof. You know this Gaussian integration. Everybody knows it? Okay. I taught it last week to my calculus class, so I'm happy that everybody knows it. Then, so if we want to estimate this integration, forget what is gamma. Just replace h with Taylor expansion. We do Taylor expansion, constant term, and suppose that z0 is the vanishing point of the first integral. Then very roughly approximation is given like that. We can throw away higher term because we'd like to know a large n limit. Then the smaller term can be thrown away. Then the constant comes out, and this is essentially the Gaussian integral. So we have this one. The negative sign comes from this minus sign. If you really want to apply it, you need to be very careful about the convergence of this integration, and you need to know these. So this says that if we want to approximate this kind of integration, we need to look for the point where the derivative vanishes. Then we can do it. To do that, of course we use Cauchy's theorem to change the contour so that it passes through the vanishing point, which is called the saddle point.
What is the technical issue?
Sorry?
You need to know that the max exists a priori? Is that the technical problem?
Yes, very technical problem. So if you want to solve this equation, you may have many solutions, and you need to find the best way, the appropriate way.
There may be many maxima.
Many local maximums.
And this method may not give you the absolute max. Is that the issue?
Not necessarily. It depends on gamma. So if there's a pole, there is a trouble. So you need to be careful to change gamma so that it passes through the closest z0 or something. And this is another thing. You need to choose that the imaginary part is constant so that the integration doesn't cancel. So you keep constant the imaginary part. So this is called saddle point because we need to pass through a col, C-O-L, the point where two mountains approaches, and we go through a kind of valley so that the imaginary part is constant and the real part is maximum. Something like that. It is not a really easy technique. So so far we need two difficulties, or many difficulties, but essentially there are two. We need to replace the summation into integration. It is one difficulty, and the second one is how to choose z0 here. But if we can solve it, so suppose that we find that kind of saddle point, then we can approximate this integration here with, so we can simply replace z with the saddle point. So the result is as follows. We call them the saddle point. Then our Jaws polynomial can be approximated by this quantity without integration or summation. So the left-hand side of the volume conjecture is given by this V function evaluated at the saddle points. So next we want to know what this means, the right-hand side means. Now, difficulty I described already, how to replace summation into integration, how to find the precise, the appropriate saddle points. And by the way, Tomotada Otsuki used so-called Poisson summation formula to, so he used a Poisson summation formula to replace the summation into integration. And yet another clever way, he also find a clever way to find the appropriate saddle points. So if you're interested in, you can read Otsuki's paper, appeared in Quantum Topology. Appeared in Quantum Topology. The title is the proof for Kashev's conjecture for not 5-2 or something like that. He used Kashev's conjecture because he is 5-2 is hyperbolic knot. Remember that volume conjecture contains, in a sense, Kashev's conjecture in the case of the hyperbolic knot. Okay. And this paper is very hard to read. I cannot. Anyway, so okay, so so far I describe very a cheating kind of analysis. So and from now I will describe some geometric method, which was already described by Abhijit, similar to the method described by Abhijit. So I think this was due to Dylan Thurston. He put an lecture notes on archive. So I hope you can find it. It appeared on summer of 2000, before the volume conjecture was published. Many works have been done before the publication. Anyway, so Abhijit put octahedron for each crossing. So and he used a vertical line. Yes, but in this case, so put an octahedron on between the crossing 2 points like this, and in our case we decompose it into 5 tetrahedra. So can you see? I hope. We have an arc from here to here, and an arc here to here, and we have a tetrahedron in between, like this. And this one comes from here, 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 and overpass and here. So this is that one, the red one. And the color is not so clear. I think this is green. Green comes from here. And we label, these are topological tetrahedra, but we call them something like hyperbolic. So remember that in the R matrix formula, we have zeta n to the I or zeta n to the m, etc. And m is in the middle, and zeta I is here. It corresponds to this arc. So we have 4 arcs around a crossing and 1 parameter in the R matrix. So we have 5 parameters for each crossing, and this 5 tetrahedra corresponds to those 5 labelings. And I will I call them by using these complex parameters because I want to identify these tetrahedra with a hyperbolic one. And then this is not similar to Abhijit's story, but we pull these two vertices up to the plus infinity, and these two to the minus infinity. And anyway, we decompose the knot complement into topological tetrahedra, and each complex is parameterized by these complex numbers. So we have one more vertices, two more positive plus infinity and negative infinity, but just forget it. Anyway, this is a kind of triangulation of knot complement by using 5 tetrahedra around one crossing. Now we want to make it into ideal hyperbolic tetrahedra, and by using these parameters. Okay, and as Abhijit described, we need, so if we want to make it into complete hyperbolic, if we want to get complete hyperbolic structure to the knot complement, we need some conditions which he called what? Gluing equation. Sorry, gluing equation. So, and we need gluing equations among these parameters. But surprisingly, that gluing condition is the same as the saddle point condition. So remember that the derivatives of V gives you some equations, and we have C of these equations, and these equations of course is the same as the gluing equation. So meaning that this xi, so these parameters corresponds to this decomposition. So we have decomposition of knot complement parameterized by zk, and we can make the complement hyperbolic if zi satisfies this equality. So this one gives the complete hyperbolic structure. Then I write what does this mean, but you know the answer. This is the volume. So this proves the volume conjecture. So you know that this gives yes, the imaginary no. The imaginary part of this one is given by, sorry, because V is given by dialog functions, and the imaginary part of the dialog roughly gives the volume of each tetrahedron. So summing up, we have the volume of the knot complement. So the imaginary part of this is nothing but the volume, hyperbolic volume of the knot complement. And because we have I here, so we have this, which is the volume conjecture. So this is a very rough sketch of the proof of the volume conjecture. So as I told you, Otsuki followed this idea to prove the volume conjecture for several hyperbolic knots. So this is not so bad. Okay. But of course, there are many difficulties. But I hope in my description that you believe the volume conjecture is true, at least for the case of the hyperbolic knots. And tomorrow, I'd like to show you more examples of torus knots. You know, the torus knots are not hyperbolic, so the situation is quite different. And in tomorrow's talk, I will first give you precise calculation of the asymptotic of the Carl-Jones and show you some relations between the Carl-Jones and so-called Chern-Simons invariant and Reidemeister torsion. So, okay, thank you. That's all for today. Thank you. Okay, yes.
Why are you dividing the octahedron into 5 tetrahedron? Why not 4?
Because the formula for the R matrix contains 5.
Oh, it's for the
Yes,
R matrix.
yes. But precisely speaking, Otsuki used Kashev's R matrix. Kashev's original R matrix, it contains only 4. So it does not contain M.
So he divided into 4 tetrahedra?
Yes. So that like you described, by decomposing by vertical line.
Yeah.
So it's a little bit more simpler.
And did he prove that the gluing equations correspond to the cycle point method? Did he use that argument?
Just writing down equations.
Yeah. I
Yes.
think that is Yoshida pointed out that that's the Neumann-Zagier potential function.
Yes, exactly.
Yokota.
Yes.
I think Yokota
Yes,
showed
Yokota,
that
yes.
Neumann-Zagier potential
Yes.
function is the V.
Yeah, V is just the, yes. And of course, the solving gluing condition is also hard. So
Very hard.
yes, how to choose the solution. So there are finitely many solutions, and you need to
You don't need
choose.
to solve it. You just need to say that this solution exists if and only if this solution exists.
Huh?
No, he needs to equate the solution of the gluing equations is the same as only they have the equality on the V. They do not know that the critical point is obtained at the same number.
So you first solve the saddle point conditions and then choose the contour, or there is a contour that you need.
Yes,
right?
yes.
So
So of course we need to check the saddle point is within the range of the changing of contour.
and it's just one saddle point that you enclose in the contour, or it depends on.
Sorry, I don't know.
Oh, I see.
I'll show you tomorrow in the case of the figured knot.
Okay.
Yes.
So this Otsuki showed this for the like 5-2 and some hyperbolic.
5-2, 6-1, 6-2, 6-3.
So what is the problem in extending it to all?
Because in the case of figured knot 4-1, it is just single summation, single integration. And 5-2, it is double. And 6-2, it is triple and more. So if you want to prove in general, you want to treat integration of finitely many.
Yeah, this is
So I think if you want to prove the volume conjecture in general, you need something more, completely new idea.
Does it help if you have the solution of the gluing equations to be roots of unity or something, like in the figure 8 knot or the Whitehead? Is the computation simplified?
No, I don't think so. If for hyperbolic knots with
Yeah.
many crossings, it doesn't matter where it is, where they are, where critical points are.
No, I mean if the gluing equations,
Yes.
if their solutions are roots of unity,
Yes.
does that help the computation for the volume conjecture? Does that, if the
How about
somehow the saddle point method, is that easier?
I don't think so.
Okay.
okay. Let's thank the speaker once again.